Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this morning we're very pleased to have Mihir Bellare from University of California, San Diego visiting us. He'll be speaking on cryptography from theory to practice. Mihir Bellare is a well-known cryptographer who, along with Ragaway, defined the random oracle model. He's also a co-inventor of the HMAC algorithm, which is widely used in industry. He's a recipient of a Packard Fellowship and an NSF Career Award. So we're indeed very pleased to have Mihir visiting us here today. Thank you.
Well, good morning, and thanks for the kind introduction. When I had given the opportunity to speak here, I had several choices for what to do, and I thought maybe people are expected to give some kind of big vision talk, but I'm not much into these nebulous visions, so this is more of a pedagogic talk. And rather than try to select one specific result to talk about, I thought I'd consider a broader topic, and which is to look at cryptography through the lens that has motivated most of my work, which is bringing theory to practice. And I apologize in advance to the experts in case a lot of what they see is something they know, and also for the fact that to make things simple, I mostly selected relatively old work for examples, but I'm happy to discuss newer work in person. So with that, I have cryptography from theory to practice, and with great thanks to Tom Ristenpart for his PowerPoint magic that makes this possible. So let me begin by asking if you used any cryptography recently, and I'll venture that whether you know it or not, you're likely to have done so. Something that was once largely of military interest is now in widespread use. You can figure this out anytime your URL changes from HTTP to have an S at the end, indicating use of the TLS or SSL protocols or some of their siblings, which are widely used for internet secure communication. So also, for example, if you make an internet purchase where you pay with a credit card, you'll be using cryptography in these ways. But even more prosaically, every time you use an ATM machine, you use cryptography. While preparing the talk, I was channel surfing and interested to find that it even shows up in James Bond movies, where one of the bad guys in this one talks about using SSL. It's hard to get more popular than that. So what is the subject about? The core problem is communication over an insecure medium, and there are a couple of different goals. One of them is data privacy, which means we want to prevent the adversary who's in control of the network from seeing the content of the communication, and the other one is integrity or authenticity, which means that we want to ensure that the data received originates from where it claims to and wasn't modified in transit. And these goals apply to pretty much all kinds of settings you could think of. For example, Bob could be a doctor requesting a medical record from Alice the database. The privacy ensures that the sensitive contents in medical information are not revealed, and the authenticity ensures that the record really originates with the database and not someone else. If you're transmitted a credit card number over the internet, then the privacy relates to the fact that the number itself isn't made known, and the authenticity to the fact that the credit card number originates with the rightful owner. To achieve these goals, cryptographers construct algorithms which process the data. So what's actually transmitted is a ciphertext, and these algorithms all operate under the influence of keys. There's several settings for this. If the key being held by the two parties is the same, we call it the symmetric setting. And we also have an asymmetric setting in which the encryption key and decryption key are actually different, and moreover the encryption key can be known to not just the adversary but any potential sender, which makes it more flexible but also more expensive. So some of the rules of the game here are that algorithms should be considered objects that are known, they're public, standardized, and present in software, so that any security comes out of the secrecy of keys. We can distinguish here between computer security, where the goal is to protect the system on which the cryptography is being executed, and in particular protect the keys from exposure due to system and software holes, and cryptography, which kind of assumes that you have a secure system underneath you and is worried about how you use these keys and build the algorithms for it to get secure communication on the network. And it's the latter that I'll be concentrating on, not because the former is not important, but just because this is a good abstraction boundary to draw on, and the fields have different kinds of tools, and this happens to be my expertise. So the questions we're interested then is how we design these algorithms to achieve whatever security goals we have, and we tend to call these algorithm schemes or protocols. What makes cryptography hard to get right is that it has to withstand attacks, and attacks, it's hard to predict how someone's going to try to attack your scheme. And failures do occur. For example, the WEP wireless protocol had some poor cryptography which resulted in pretty well-known failures. Failures are costly for two reasons. One is the publicity, negative publicity, and the other is changes to software which are expensive. So a lot of the goal of cryptography is to try to prevent failures. A classical way to do that is to begin by analyzing a scheme and then attempt to break it. And if you succeed in breaking it, well, you iterate and until you can come to a point where you have a scheme of which you feel reasonably confident. The people who attempt to break these schemes are called cryptanalysts, and their expertise is to mimic attackers and try to figure out what the weaknesses are. And eventually one hopes to come to a scheme where these experts don't really have a way to break it. What one needs to understand about this process is that the confidence you're getting in security is somebody's view that they themselves can't find an attack. It's not an indication that attacks are guaranteed to be absent. And I can raise certain concerns about this approach. One of them is that we achieve our confidence by trust in experts. That's not necessarily a bad thing, but some of its difficulties are that it doesn't scale well. There's far fewer of these experts than we have schemes being created. So for example, at Microsoft, you're not lucky to have Niels Ferguson, who's one of the experts in this area. But imagine if every single crypto-containing product had to be passed by him before you deployed it. It'd simply become a bottleneck in the process. So we'd like things that scale better. Unfortunately, many people think that they can do cryptanalysis quite well and try to do it on their own, and then they get it wrong. So the alternate methodology I would like to consider begins with the people here at MIT. And when you start using it, you probably begin the same way as before. You design some scheme, you try to break it, and you iterate until you get to a scheme that seems reasonable, in the sense that you probably can't find an attack. But you don't stop there. What the methodology that they've developed can do is offer you some kind of proof that not only can a certain person not find an attack, but there's some sort of evidence that other people are not going to find it either. And the advantage of this is that you get some sort of verifiable certificate of security which you can check and allow other people to check, and thereby gain confidence in the algorithm. So there's a few things there that I'd like to explain in more depth about this methodology, in particular why it says and what it means that nobody is likely to, not that they actually can't, and secondly how you can possibly get proofs for security. So we start with some desired end goal, which is to design a scheme I'll call Y, and it might be for some task that we want to do over the internet, like encryption of data or authentication of data. Now, historically, people may have approached the task of designing the scheme by simply sitting down there and starting to write some algorithm. But modern cryptography doesn't do that. What we have is a set of tools or problems from which we start and view those as something we call atomic primitives. There might be mathematical problems, or there might be certain constructs that have been engineered by cryptographers. As an example, the factoring problem is that I give you a composite number and ask you to find the factors. Well, this is pretty easy for a small number, but once it gets big, it's hard to figure out how to do it. And this is a task that, as far as legend goes, had even daunted Gauss, and certainly no one's done any better so far. The difficulty with something like this is that it's not a cryptographic solution. It's a mathematical problem to factor a big number, and we need to see how we can actually use that to encrypt a large file. So what cryptographers do is transform these atomic low-level primitives into high-level ones. And when we talk about proofs, or in particular about security, we're concerned with the security of this transformation process. Historically or empirically, it turns out that atomic primitives tend to be much more stable and secure than the schemes we build for them. There are relatively few of them, and although they're sometimes subject to attack, they are studied in depth by experts, and we can have reasonable confidence in them. But the number of schemes that people are designing on them is huge. In Microsoft, there are probably hundreds of pieces of cryptography at this end of the spectrum, but they all use this transformation process starting from a small set of primitives. It seems that we tend to put bugs in when we do this transform. And what the proof process does for us is say that this transformation process works in the sense given here of a reduction, which says that if you give me any way to attack this scheme by some adversary I'll call A sub y, then I have a way to turn it into an adversary that attacks this scheme. Read backwards, it means that if you have confidence in the atomic primitive, it automatically translates to confidence in the higher level primitive. And the advantages of this are that not that you've done away with cryptanalysis, but that you've confined it to a smaller set of things so that the cryptanalytic talents in the community are not kind of spread out and wasted over too much stuff, but can be used on the things that actually matter, and the rest of the confidence can come mathematically. I'd like to point out that sometimes people who look at proofs are viewed as anti-cryptanalysis. That's really not my perspective. What I rather believe is that cryptanalysis is an important and valued trait in the community, and what proofs do is leverage it better rather than allow it to be kind of dispersed across too many things. One of the central pieces of what this methodology is about is that when we use the term of breaking something, it has a precise definition underlain by a precise model. And the consequence of that is that we know what assumptions we're making and against what class of attacks we're secure. So you get a much better understanding of what kind of security you're getting from this process. Provable security isn't a panacea. Niels will give you many examples of provable security schemes he's broken. Some of the reasons things can go wrong are that although you did provide a formal model, it didn't capture some threats that were later seen to be relevant. A neat little example of this is WinZip encryption, which was shown to meet certain security notions in theory, but they didn't cover the attacks that could actually be mounted in the system, and hence was broken. Another example is attacks that go outside the model by looking at things like the time taken by your program to execute, or the variation in its power consumption and things like that. And if your models didn't take this into account, well, then it'll fall to these threats. You have to implement it correctly. It doesn't help to have a proof if you don't. You do assume your atomic primitives are good. If they aren't, and that happens sometimes, the most spectacular case recently was when collisions were found for hash functions, then of course all bets are off. If you get a proof, you better get it right, otherwise it's also worthless. One of the things I often feel about the way we do proofs is that I can't verify some of the proofs in the literature. It's dubious how valuable they are in this case. But even given all these caveats, I do feel that provable security is valuable. On the whole, it can give you increased confidence in scheme security, and it's something that people can learn to use and be educated about in a way that's more difficult for an art like cryptanalysis, which is somehow requires just a kind of cleverness which you don't necessarily need if you just have to check proofs. Provable security is good in that it makes clear the models and assumptions in use and can be communicated. As a rough analogy, in case you don't know about this area much, a proof of security is very much like an NP completeness proof. It's not telling you, if you remember the story from Gary and Johnson's book, your boss asks you to solve some problem, and you come back the next day and you say you don't know how to do it, and he's not very impressed, but then you say I don't, but nor do all these famous people, because it's NP complete and equivalent to all these other things. It's somehow the same principle. You're seeing that your scheme is secure, because if not, then a lot of the problems that a lot of clever people like Gauss have studied would become easy, and we don't believe that. Okay, so that was kind of a background. My story begins here. I was a graduate student at MIT, where we learned all about the theory and the beautiful frameworks for proofs and all kinds of notions, and generally were given the impression that we could solve all the world's problems. And after that, I got a job at IBM in a group which was working on a high-speed network, and they felt like they wanted a cryptographer. And what I found was that things were extremely different. The kind of cryptography and words we were seeing in practice were things like block ciphers, DES, things like CBC encryption or MAC, lots and lots of standards for doing cryptography, protocols for session key exchange. And when one looked to see what the theory had to say about this, well, the answer was basically nothing. None of these things were covered in theory. A course at MIT didn't even mention DES. They didn't seem to have any knowledge or interest in these kinds of topics. That didn't mean that they were idle. There was an entire framework of cryptography in theory based on assumptions like one-way functions, achieving goals like zero knowledge, talking about proven secure public key encryption and signatures. And when one looked to what that was happening with that in practice, well, basically nothing. No one was using that or seemed to be influenced by anything like that at all. And this was the gap that kind of motivated our work. And my work with Phil Roggeway was about bridging this gap. And what we did was provide schemes for which we could give proofs, but which reflected practical constraints and problems in a way that made them usable. And if one wants somehow a very simple, let's say, oversimplified view of what the source of the gap was, you could say it's effectively performance. So theoretical schemes were slow, and practitioners needed things that are a lot faster. But this gap wasn't something that you could change by writing faster code or something like that. The gap was enormous. It was factors of millions and billions and more than that. And what we found is that the gap didn't arise from say, levels of detail, but from major cultural, what I would like to call cultural differences in the way these two communities looked at things. And I'd like to examine those differences and what we have been trying to do to change them to bridge this gap is kind of the focus of my talk. So one of the main and first differences we found was in what people viewed as appropriate atomic primitives. So remember, the atomic primitives are the things you start with as given before you start building schemes. In practice, we saw a set of primitives that were built by what people called the confusion-diffusion paradigm, which means that they were engineered by cryptanalysts who studied them and tried to make them secure, and they included things like block ciphers and hash functions. What theory was using is things arising from mathematics, like one-way functions, factoring, discrete log, RSA, and things like that. And if you ask the theoretician, their general view of what practitioners use as primitives was quite negative. They thought of them as ugly objects which really shouldn't be looked at and had no place in the theory. The answer of the practitioners was that, well, if you think our stuff is so bad, why don't you try to break it? And by and large, that turned out to be true in the sense that these things were not broken, and their performance gap between these things was incredible. So it would seem unreasonable to say that this group of people should move to this viewpoint. Now, the reason I call this a cultural gap is that the theory community hadn't looked at what the practitioners did, analyzed it, and decided that it's bad. It was at some sort of level of taste that they viewed these things as something that just shouldn't be considered. And it reflects probably just the origins of this community in complexity theory and mathematics, whereby engineered objects which are built by hand based on principles that are maybe sound but held implicitly by experts was just somehow not to their taste. Now, another confusion I might like to eradicate before I go on is that from these call-outs you might think these groups of people actually talk to each other, but they never did that. Whatever I've seen here are things that they've said to me when I ask them questions or communicate to each other. So what Phil and I did is to bring these types of primitives into the fabric of provable security by supplying appropriate definitions and models under which you can use them. And once you do that, what we found is that you can build cryptography just as well on the back of confusion diffusion as on number theory. And this is a gap which, in fact, one could spend an entire lecture on. In many ways, once you start looking at it, you see that these primitives have greater strengths than the ones here. They have different varieties of strengths, ones which in some cases are harder to capture by models, but which seem to be present. And also they have strengths simply due to the fact that cryptanalysts just have much higher targets. They expect things in some sense to be much stronger than in this domain. And that's why things are often viewed as broken here, which may not really reflect weaknesses. I'm happy to say that subsequent to our work, this has become relatively standard. So by now, a lot of papers in the literature use our assumptions and methods to work off these kinds of primitives and build provably secure schemes on them. A second cultural difference we found is in concrete versus asymptotic security. The way theoreticians model security is to have a parameter called a security parameter which goes to infinity, and so that any scheme is actually a collection of schemes, one for every value of this parameter, and the advantage of an adversary, which is its success probability, is a function of this security parameter. In practice, however, many of the primitives have no parameter going to infinity. The AES block cipher has 128-bit keys and input-outputs, and that's all there is. What theoreticians dub security is to say that they have schemes where polynomial time adversaries can't break it, in the sense that as the security parameter goes to infinity, so does their success probability. Now, they have a specific definition which says that the rate at which this function goes to infinity is something. For example, in particular, it's less than the reciprocal of any polynomial, and that's called a negligible function. The difficulty with this approach is that if you want security like practitioners do, who say, well, we want to know what happens when you have an attacker that has 2 to the 50 running time, and we want to make sure it doesn't have this much success probability, is in principle this tells you nothing, because all it tells you is that as the security parameter goes to infinity, things get reasonable, and it's not clear what polynomial time is in the context of 2 to the 50. Now, again, one of the reasons I call this gap cultural is that it's not as though there's an enormous technical difference between these two. It's more that the people who developed theory had their origins in complexity theory and viewed cryptography as an extension of complexity classes like P and BPP and NP. And to them it was natural to translate that framework into their definitions here, so that you got polynomial time adversaries and security parameters which function just as the length of the input in complexity theory. And they just somehow didn't feel like they could develop a theory around things like this. And our contribution there was to to bridge this gap by producing provable security statements in this type of framework by appropriate models and definitions and results. Now again, this is a perspective, this gap is something one could spend a whole lecture on, but it is kind of interesting in the way that it developed. Once the culture of theory was fixed to this, a large fraction of them followed it, continuously after that, without trying to make a change. But nonetheless, some fraction of the community has since switched over into our viewpoint into concrete complexity. In particular, for example, work on pairing-based cryptography employs this. Now, in this, another way to look at this gap, in my perspective, is to consider the theoretical computer science has people working in complexity theory and in algorithms. Algorithms are people who care about whether an algorithm runs in time n cubed or order n squared log n, which are highly different to them. Complexity theorists largely just care about whether something is polynomial time or not. In some sense, cryptography never developed an algorithms community. It stayed a community where people were interested in polynomial time as opposed to finer-grained measures of efficiency. It's also, you can see cryptographers improving efficiency and giving algorithms which are computationally more efficient, but when they disregard concrete security, that actually turns out to be effectively vacuous. And this doesn't seem to be understood to too great an extent. Anyway, a final gap here was in goals. Theory tended to focus only on public key cryptography, in public key encryption and signatures, and then lots of fascinating higher level goals like the ones listed here. But 90% or more of the cryptography that actually goes on in practice is in the symmetric setting. And there are also problems like session key distribution, which I found seems to have more incorrect protocols out there than any primitive I've seen in cryptography, and was not being addressed in theory at all. And the theoreticians viewed symmetric cryptography as kind of a special case of asymmetric. Isn't this just something stronger? In fact, that view isn't even correct in the sense that even definitionally they're not the same. But the performance gap is huge due to the fact that you can use confusion diffusion primitives. This gets thousands to tens of times, 1,000 times faster than the most basic asymmetric encryption. So our focus was on developing solutions and definitions and models in this domain. Okay, so the rest of my talk is a bunch of examples to illustrate these ideas more concretely and talk about some specific results. And I guess I'll go through as many of them as you have patience for and then stop. The first one is about encryption. So I want to first talk about the basic underlying primitive, which is block ciphers. So a block cipher is just a map which, under the influence of a key, transforms an input of some block length b, say 128 bits, into an output of the same length. And if you have the key, you can not only go forwards but backwards. DES, for example, has certain parameters of key and block length. The modern AES has different ones. And how do these things work? Well, there are that's again a topic for a book or something. But here, for example, is a high-level description of the AES cipher. And as you can see, it just kind of operates through rounds, each of which mangles the bits of the input under the influence of the key. And here, this one relies on numerous subroutines that I'm not going to talk about, but maybe it's enough to get some kind of flavor. Traditionally, when people have discussed security, what they mean by this is security against key recovery. All the security comes from the key, and what we want is if an adversary has input-output examples of the cipher, it should have a hard time figuring out the key. One of the things that we'll do is update this view, and that's part of our push to develop models for atomic primitives which are useful to show security of the end goals. We'll have to update this one. Now, naively at least, a block cipher allows you to encrypt. If I have a B-bit message, I can encrypt it by applying the block cipher into this key and send it to Bob. So why aren't we done? Well, just for a simple pragmatic reason that you can, by this method, only encrypt a 128-bit plain text, and that's not what you want. You want to encrypt longer messages. So we do that by something called modes of operation. And this is where we can see the sort of paradigm that I've been discussing emerge. In this process, we view the block cipher as an atomic primitive, and we are aiming to construct by some transform some primitive that's more directly useful for applications, and which we call a symmetric encryption scheme. So, and that too is a process that takes a key and processes an input to an output, but the difference from a block cipher is that the message has arbitrary length and the process could actually be randomized. Now, there are numerous choices for how we might do this transform and build the encryption scheme, and here are the most common ones. The electronic codebook mode is the most obvious. You just break your message into blocks and apply the block cipher on each block. A little more involved is cipher block chaining, and its most interesting feature is that every time you encrypt, you pick a random number anew, and that random number influences this process through chaining as shown in the picture. The ciphertext is longer than the plain text by including this random number, and it turns out, although it's not shown here, that if you have the ciphertext and the key, you can decrypt this thing. So then the questions we would have about these things are they secure? Is one better than the other? So forth. Now, it turns out that CBC encryption is, in some sense, the world's most used encryption scheme. That's the one that's deployed, or some extensions or variants of it are deployed pretty much everywhere, and that's how things get encrypted. So what Phil and I were interested in was understanding how secure this is, since its impact on real-world cryptography is really pretty immense. So to answer that question, here's where we kind of step back to take a theoretical perspective, is we wanted to first know exactly what one means by something being secure. The traditional idea was the same as for the block cipher, which is that if you had some inputs and outputs, you couldn't figure out the key. Now, under this metric, electronic codebook mode is actually secure, because having input and output examples and trying to figure out the key is no different for the encryption scheme than from the block cipher. So if you believe you have a good block cipher, this is a good encryption scheme. And yet practitioners for a long time had already understood that electronic codebook mode is bad, and looking at why it is useful to illustrate that security goals are things that you need to kind of formulate with more care. So let's do that. So across the lake in Seattle, they're voting, for example, on a proposition which is worth quite a bit of money, and let's say that the vote was being encapsulated in the following way. So let's say you submitted your ballot at some polling station, and let's say this polling station shared a key with some tallying center, and when it got your vote, it encrypted it and sent it across. And let's say that they encoded votes as one block strings. So ECB now simply comes down to application of the block cipher. So if Elaine's vote was yes, this is what would get transmitted. And let's say Jerry had some other vote, V2, we don't know its value yet, then this is what will get transmitted. What you now see, though, is that even without knowing the key or without computing it, it's very easy for this person to figure out what this person voted, because this process is deterministic, and if V2 was equal to Y, C1 would equal C2, and otherwise it wouldn't, because this is a permutation. So just by examining whether or not these two things are the same, all security here is lost. Elaine can completely figure out what Jerry's vote is. So this is the kind of thing that we consider a flaw in the encryption scheme and would like to avoid. So that kind of throws this encryption scheme out, but we'd like to analyze other ones. Now, in order to go further with that, though, we'd like to pin down more precisely what the security goal we just discussed is. And for that, cryptographers create formal models, and I thought I'd try to illustrate one of them. So this is the definition that Phil and I gave for symmetric encryption, and it just imagines a game in which you have an adversary, and its interaction with the encryption scheme is via a certain oracle. The adversary can produce not one but two messages of its choice and ask the oracle to encrypt, and the oracle will encrypt not both of them but one of them. The only thing is it won't tell the adversary a priori which of the two it's encrypting, and the encryption is done under a key the adversary doesn't know. At the end of this process, the adversary can make many such queries. At the end of that, it's going to try to figure out which of the two was being encrypted. That's all it's trying to figure out. Now, this is a relatively simple extension of the same definition given by Goldwasser and Micali in the asymmetric setting, but there are some differences in the symmetric setting, in particular the fact that you need these oracles because the keys are hidden. We assign a measure of success to the adversary. It's not the probability that B prime equals B, because that can always be a half by a simple guess, but some reflection of the extent to which this probability exceeds 1/2. Already here we're seeing a concrete security approach, because in theory nobody defined this function. They would just say that the difference of this probability to 1/2 is negligible or something like that, and merely writing this down will enable us to do more with that. So this advantage measure is going to depend on a number of things, like A's strategy, but also on how many queries it makes, how much computing time it has, and so forth. And when we talk about security, I'll use this terminology, indistinguishability under chosen plaintext attack, to reflect the type of goal, and loosely speaking say that security just means that this number is small for any adversary whose resource usage is practical, doesn't exceed practical amounts of running time. This is not a formal definition because it doesn't define what small and practical are, but that's kind of essential to a concrete approach. In reality, security is not a Boolean attribute. It depends on the resources an attacker invests. And in theory, you would say something like, well, the attacker's success probability is negligible and that's security, but then it's difficult to translate that to practice. Yeah?
What if the attacker sends M0, M0, and then M1, M1, and then M0, M1?
Sure, so it could do that, and if it sends, if it sends M0, M0, it's get back. The attack here is talking about will work if the encryption is deterministic. So that's a great point, and in particular it proves that in some sense, this is why this captures ECB failing. So one of the implications of this is that any good encryption scheme has to be randomized. So when you send M0, M0 the first time, and then in your third step you said to again send M0, M1, the coins used in the two cases would be different. And so even if you twice encrypt the M0, it won't look the same. Okay, so that kind of loosely says what we mean by secure encryption. We need a similar definition for the block cipher, and it won't be security against key recovery. It's what's called being a pseudorandom permutation. And here I'll skip the precise formulation, but the intuition is that the input-output behavior of the block cipher resembles that of a random permutation. The important caveat is only to someone who doesn't know the key, but only sees input-output examples. And this is the definition that was kind of lurking in theory literature, but we pulled out and made concrete, and now underlies a large fraction of block cipher usages. So we saw that electronic codebook mode is insecure, and we also saw that CBC is highly used and potentially is more secure due to the fact that it's randomized. But it would be nice to know whether there actually are attacks of the form that there are in ECB. And roughly speaking, the answer we gave in our work on this subject was that it is secure, meaning that it meets the notion of security we just outlined, as long as you assume that the block cipher is itself good. So this gives us some confidence that this notion is right, and supports the fact that if you're using it right now across hundreds of thousands of platforms out there, it actually works. Now, just as a recall, underlying these two things here are the formal definitions we talked about. This is the formal security goal for encryption, which captures very strong security requirements. And this is the assumption we make on the block cipher, which is stronger than usual, but is necessary to get any kind of conclusions about the usage of the primitive. Now, that's kind of an informal statement that doesn't give you the concrete view. And this is how it would look in a concrete security setting. So here, the theorem doesn't say something about security or not. It just gives you a numerical relation between the success probabilities of adversaries. It says that if you give me an attacker on the encryption scheme, and it has some resource usage, it sees some number of encryptions of messages of some length and has some running time, I will build for you an attacker against the block cipher, and their successes are related in this way. And you read that as saying that as long as this quantity is small, meaning the block cipher is secure, the inequality tells you that this is small as long as the resource usage of your attacker doesn't get to be too big. And the nice thing about this is that you can get numbers out of it. So for example, if you encrypt this many messages of this length and you want security against an attacker with this much running time, you can plug it into the formula, and under appropriate assumptions on the block cipher, and let's say we're using AES so that we have 128-bit block lengths, the formula will tell you how much success probability your adversary will have. Yeah?
It seems that this chart would look really bad if you used it on DES, no?
That's right. Yeah. Okay, so I guess I should say something about that. There's a term here that in some sense becomes the bottleneck to getting good security out of this. This term is not an artifact of the analysis. As long as you're targeting this type of security notion, this reflects birthday attacks that can actually happen. Now, you might debate whether those attacks are important in practice, but if we take the position that encryption is something that needs to be deployed in a way that's kind of application oblivious, it should work for any application, then they're important. And this term grows fast enough that if you use DES, you'll get very little security out of it. In fact, even with AES, you probably get less out of this than I'd really like. But anyway, so in conclusion, this sort of exemplifies the whole path we followed. It talks about how we used confusion diffusion primitives here, the block cipher, and made assumptions about them. We were able to analyze symmetric cryptography used in practice, get provable security results about it, and in concrete security settings that gave us back numbers that we could interpret. Okay, my second example is about integrity of data. So here what's happening is that the message is being transmitted, and Bob wants to make sure that when he gets a message, it really originates with Alice and not someone else. To do that, Alice attaches a tag called a MAC, also computed under the secret key that they share. Note that the message is transmitted in the clear. We're not trying to achieve security here. We won't go into this formally, but roughly the security goal is that it should be hard to produce a MAC of a message without knowing the key. So this functions as a kind of fingerprint which only the holders of the key can produce and vouches for the fact that the message is authentic. Now, historically, MACs were built based on block ciphers, and in particular, the DES-based CBC MAC was one of the first and most widely used ones. But later on, hash functions started appearing, and this character should be a membership symbol. I guess my fonts on two machines are not the same. So, yeah. So, hash functions had the nice property that they were faster than block ciphers that were present at the time in software, and so people wanted to look at them for a base to use here. Now, it may be a little useful for what we're going to do to say a little what hash functions look like. Hash functions themselves are built on the principle we've seen before of transforming some atomic primitive to a high-level one. The atomic primitive there is a compression function, and it's repeated a number of times in some way to hash data of arbitrary length. Their standard property of the hash function is what's called collision resistance, which means it should be hard to find two different inputs with the same output, even though mathematically, of course, these kinds of collisions abound due to the fact that the hash function output is a fixed length, like 160 bits, and inputs are arbitrary length. So when you start thinking about using hash functions for the purpose of message authentication, the basic bottleneck you have is that these primitives don't take keys, and message authentication depends crucially on use of a secret key. So how do we put a key into there? Well, various proposals like this were made, but eventually my colleagues at IBM, Canetti and Kravchik and I came up with this proposal called HMAC, and it's quite simple. All it does is prepend a key to the input and hash, except that it then takes the output and repeats the process, so it hashes twice. And there are a couple of things about this design that made it attractive. One is that we could prove some sort of security properties. We could prove that it's a secure message authentication code under appropriate assumptions, and the assumption here was what people was assuming typically of the hash function. It's collision resistant. And secondly, we also needed an assumption on the underlying compression function that it satisfied a notion called being a pseudorandom function, which you don't have to know exactly what it means in depth at this moment. So additionally, however, HMAC was practical in the sense that it was efficient, just 2 applications of the hash function, easy to implement because it made only black box use of the hash function. And possibly these are some explanations, barring luck, I suppose, of the fact that HMAC is now widely used. Microsoft uses it, and it's the only, I understand, what's called automatically approved to implement MAC. It recently became a government standard. It was used in IPsec, TLS, SSL, pretty much everywhere. So with this kind of deployment, security becomes crucial, and the story of HMAC interestingly continues into quite recent times with the fact that hash functions turned out to be a lot less secure than we thought. So you already saw Professor Wang on a previous slide, and she showed that MD5, which was a hash function which HMAC is used quite broadly, is not collision resistant, and neither is SHA-1, this may not be. Now, when people tried to extend those attacks to HMAC, they found that they couldn't. So the attacks don't actually break HMAC. The keying and the structure somehow prevents that. But it had an interesting theoretical consequence, which is that the result justifying security effectively became vacuous, not because the theorem was wrong, but because one of the assumptions was false. You can view as what Professor Wang is saying is simply that since the hash function is not collision resistant, this theorem effectively says false implies true, which is always true. So I returned to this a little bit after these attacks, based on the fact that people were kind of questioning, even though HMAC wasn't broken, whether the lack of a proof should mean that one should consider removing it as a standard. And what I did was prove that HMAC continues to be secure even if this assumption isn't true. So merely the second assumption is enough to guarantee security. The good thing about that is that the second assumption is not refuted by any known attacks. And so this re-established a proof-based guarantee, and at least to some extent was influential in maintaining confidence in the standards. But I think it would be unrealistic to end there. I should note that even given this proof, and even given the fact that HMAC with MD5 is not completely destroyed at this point, I definitely don't encourage its use. Cryptanalysis of it continues and gets better and better, and I personally don't believe that it's going to stand up in the future. So you do want to make sure that you have hash functions which are likely to have the property you need for the proof to be true, and this seems to be much better with later hash functions such as SHA-256. Yeah?
Where does the proof fail if HMAC MD5 fails? Is it the secure pseudorandom function that would fail? Or you don't know?
Oh, in that sense, the situation that was before comes back, in the sense that if you simply had some attack showing that MD5, its compression function is not pseudorandom, you wouldn't necessarily break HMAC. So again, the proof is not capturing everything that's there. But conceivably, I would imagine that HMAC MD5 will eventually itself just be attacked somehow.
That's because you think that the compression function may not be pseudorandom.
In particular, yeah. Although I think that could be proved before there's an attack. Yeah?
Since 96, hashes have got rather slower when they got more secure. And of course, the date implies that this happened when exporting hashes would not send you to jail, and exporting crypto we would send you to jail.
That's right.
To do it again in this century, will you still use hashes as a basis for MACs?
That's a good point. In some sense, nowadays, for example, even the performance gap is dropped. So AES is much faster than DES was, it's not clear there would be such a strong motivation anymore. So at this point, use of HMAC is largely entrenched, and so okay. So I guess I can quickly do my last example, which was asymmetric encryption. So here we're in the public key setting, and Alice wants to encrypt a message. She can do that given kind of public information about Bob in the form of, you can think of like a public phone number, which Bob can decrypt with a secret key. And again, our goal is privacy. Largely speaking, in practice, we use RSA encryption. The public key here is a number called a modulus and an encryption exponent. It won't matter much if you don't know how these work. And there's a corresponding secret key over here. So when we tackle building encryption schemes with RSA, we need to make use of the mathematical RSA function. What cryptographers like to think of this as is what's called a one-way trapdoor function. This means that if I give you the public key, the modulus and exponent, and I give you an input x, it's easy to compute the value of the function, which is defined by raising x to the power e and then doing that modulo n. Similarly, if I give you the decryption exponent and the modulus, it's actually easy to go backwards and go from f of x back to x. But as long as you don't have this decryption key d here, it's currently not known how you can reverse this process. Now, I'd like to add there one important technicality, that our understanding, or at least the formal assumption about this, relates to when x was chosen at random. If I choose x at random and give you f of x, don't give you the decryption key, no one knows how to go backwards. Now, when RSA was introduced based on the Diffie-Hellman type paradigm, it was generally thought that we've solved public key encryption because that is encryption. Just let the encryption be this, and well, you can encrypt and decrypt, and the adversary can't reverse the encryption process without the secret key. The difficulty is that this function, although you cannot get m back from f of m, can reveal partial information or some pieces of information about the message, and that's not what we want for good encryption. So that puts us back in the position we've seen many times by now, which is that we want to create an encryption scheme viewing the RSA function as a low-level primitive and the encryption scheme as a high-level one. And the question is, how do we actually do the transform? So one thing that will be necessary is randomization, because without that, we will not meet the kind of strong security goals that I talked about in the symmetric setting and that extend here. Now, in theory, this problem was solved using something called hardcore bits, and they can tell you that they can provably encrypt with RSA in this method. But when you look at this from a practical perspective, you hit performance bottlenecks. So every encryption here, each RSA operation only encrypts one message bit. If I have a 128-bit message, I have over 100,000 bits of ciphertext. And plus I need a lot of RSA operations. So what practitioners said is, let's do something very simple. We know that you can't let the message be the object to which the RSA function f is applied, so let's throw in a little bit of randomness and pad out the message with that and then encrypt. Well, across the fence, the comment about this was not that we know how to break it, they didn't know how to break it, but to be careful about this, because it's no longer the case that you can prove security of this method based on the assumption we'd like to make about RSA, which is that it's one way. So if this works, we don't really understand why, and that's kind of a cautionary way to look at it. Well, as long as, nonetheless, for performance reasons, this turned out to be widely deployed. It was a standard introduced by RSA security, and from then into pretty much every standard out there, and this is what gets used. It turned out that the pessimists were right in this case. So eventually attacks emerged and showed that there were different ways to compromise PKCS. One of these is what's called a chosen ciphertext attack, whereby an attacker with some sort of limited access to a decryption box can break the scheme. And this turned out to be relevant to the use of PKCS in SSL, which is why this CERT advisory went out. But later, even stronger, what are called chosen plaintext attacks emerged, where certain types of messages could simply be recovered from the ciphertext. What we proposed as an alternative was something called OAEP, which follows the PKCS paradigm in saying that we only want to apply F once, and we want to be able to put a large number of message bits into any in a single encryption. So what it does is it takes the message, adds some redundancy, and then takes a random number here. This is the randomization, and processes as shown based on a couple of public functions to produce some output, and then the RSA function is applied to that. Okay. So what was good about this is that it had some kind of provable support. Under the assumptions that theoreticians like to make, which is that RSA is one way, and under another assumption that I'll discuss more in more depth later, which is that these functions are what are called random oracles, we could prove security against chosen plain text attacks. It turns out you can also prove security against chosen ciphertext attacks, which is what you need to prevent the kind of thing that Bleikenbacher talked about. Now the benefit of this is that it meets both the practical and the theoretical constraints. On the efficiency side, it's as efficient as the broken scheme that the practitioners wanted, but it had some kind of security proof. And again, that turned out to be attractive for usage. So OAEP is also in a whole bunch of standards and software across the world and so forth. Now, this story has a kind of embarrassing component as well. In our original paper, we had actually claimed not only this security, but security against these stronger attacks. And we got that wrong. Luckily for us, the fact itself wasn't false. So other researchers filled the gap soon after it was pointed out. But I think it reflects something about proofs, and also the fact that in those days we just had so much to do that we were going really, really fast, and we kind of missed some things. So I'd like to talk a little bit about the methodology behind that result, and particularly this fact about random oracles, which have become another rather widely used method. So the random oracle paradigm was something that Phil and I created exactly in order to bridge this gap between theory and practice, where you didn't seem to be able to produce schemes of the kind of efficiency that practitioners needed and yet have security proofs. And what we noticed is that the building blocks used in practice had properties that were not captured by theoretical definitions but seemed very strong, which is in particular that things like hash functions were built to have random behavior, and we wanted to try to capture that. So we created this model based on some inspiration by Fiat and Shamir, where you have access to a box which implements a random function. That just means that when you call this, think of it as a piece of software somewhere out there on the internet, it'll simply return a random number, except that it's nice enough to be consistent. If you twice ask it the same question, it gives you the same thing back. So this is in fact a complete noise box. It does nothing of any discernible value, it just gives you random stuff. Nonetheless, this turns out to be just about the most useful cryptographic primitive you can imagine. And what we did is show how large numbers of schemes can be proved secure in this model. Now, at first glance, that's quite useless because the random oracle is effectively a thought experiment. So our next step was to say that when you want a practical scheme, you replace this random oracle with a hash function. And in that way, we were able to get highly efficient schemes with security proofs in this model. The caveat from a theoretical perspective is that the security proofs applied in the random oracle model, they didn't apply to the instantiated final scheme. And this aspect has led to the random oracle model being highly debated and controversial. In particular, people have shown that it's possible to find counterexample schemes which are secure in the random oracle model, but once you use the hash function, they fail. And that might sound like a problem, except that these counterexamples are all artificial. They're kind of built to fail. And real schemes, this doesn't seem to happen. The random oracle model is probably one of the most popular things we've done. It's used enormously. Just one such instance is it was used for the first IBE scheme. By and large, the practical schemes based on it have not failed. But the theoretical questions it raises are quite interesting because nobody knows a really sound theoretical way to bridge the gap between the random oracle model and the instantiation. And this kind of reflects to some extent Phil and my philosophy, which is that when we had a choice between choosing between theory and practice, we chose practice in the sense that we were willing to sacrifice the proofs to the largest extent, to the minimal extent possible, to bridge the efficiency gaps. And thereby we created these kind of hybrid methods. I don't have much to say about where things are going, but my particular interests are in pushing cryptography to the point where it's even more aware of what goes on in practice in software and systems than now. And another direction I'm interested in is in making theory more understandable and proofs more verifiable by tools to do these things. I'm sorry I haven't had time to talk about my more recent work, but I've worked a lot on many of these topics, and I'm happy to get into that anytime in offline. So I'll stop there. Thank you. Yeah?
You said several times, get some randomness. Now, where do you get randomness in a real system?
Yeah, that's certainly...
The bad guys can't guess.
That's right. So that's certainly one of these sort of problems where, it's not clear how to do it. So of course there are all these standard heuristics. You take system parameters and you hash them and you do things. But yeah, these things presume high quality randomness. So that's another one of these gaps that it's not. Yeah?
So you mentioned random oracle. Is that a typical pseudo-random number generator with a potentially random seed or something?
So the random oracle is a thought experiment. So it's not pseudo-random, it's perfectly random. So when you use a pseudo-random generator, you are approximating it to a certain extent, but that approximation is something that I don't know how to capture in any formal way. So heuristically it might work, but there are somehow no guarantees about it. Okay? Yeah? Sorry.
In the beginning, you defined sort of the difference between, I believe, the security analysis and then the cryptography, where the security was looking at viruses and other ways to get things, and you said you were going to concentrate on the cryptanalysis. Although then later on, you did mention some attacks that use like the looking at the electricity changes, and so how much in practice can you really separate those two?
Yeah, that's a good point. So in practice, they're harder to separate than in theory, and but there's a lot of work at both ends, I think, in pushing theoretical models deeper into systems to capture this, and on the other side to make cryptography aware of what's going on in systems. For example, one thing I've worked on is protecting against break-ins by forward security, where the key evolves with time. So if the system gets broken into at a certain point in time, you only lose the current key. But this is a huge area of problems and issues for security in general, where largely things are open. Yeah, Charles, you were saying something?
Yeah, I was just going to comment about the number of co-authors in the paper.
Oh yeah. It was a merger, so these things happen. Okay. I guess that's it then.